So you're stuck real bad, but don't be sad. Mark is here to help you escape from Alex. There's gonna be some yummy pie filling.
Well, howdy, everybody. Howdy, Mike here. And today we're going to do another topic. This time in chapter 5 of the OpenStax book, we are going to do a basic calorimetry problem. This is actually a problem that we do an experiment with in the place where I work and teach. Well, it should be work and teach aren't two separate things. But here's the way the problem goes. We've got some sort of sample that we place into water, and we want to know its specific heat capacity. Just zooming to the end of the problem. We're going to, apparently it's made of aluminum. Okay, that's good to know. Just as a little bit of good prejudice, metals usually have pretty low specific heat capacities. They're good conductors. As a matter of fact, the denser the metal, the lower the heat capacity, and the less dense, the higher. I said that the wrong way. The denser, I said it the right way. The denser the metal, the higher the heat capacity, and the less dense, the lower the heat capacity. But nonetheless, something like water has generally a very large specific heat capacity. And I see that in the problem, they've left that out. But basically what we're going to do is we're going to take this sample here and we're going to plunk it into some water. And there's going to be a temperature change because the sample, I guess, is warmer, right? And there it is. 95.7 degrees, so almost boiling. And then the water is cool or a little bit above room temperature, and they're going to equilibrate, and they're going to get to a point where they're at the same temperature. I misspoke. Actually, the initial temperature is 22, so that's about room temperature, and they're both going to end up at 26.5. Okay, now, first of all, before I start thinking about how to approach this, the master equation that we're going to use is Q, that's heat, equals M, mass, C, delta T. I can't write deltas on my keyboard, so if I just say DL, that's like a delta, that's a temperature change. Now, I'm a unit freak, all right? If the desired result is Q is going to be in joules, then we would go ahead and say, okay, what are the units of everything? Units of this is going to be units of joules. That means that the units of the other side of the equal sign also have to have the units joules. So, mass is generally in grams. I don't know if they gave it to us in grams, but we'll have to make it into grams. All right. We've got masses in grams. So cool. Now, what's delta T? Delta T is going to be temperature difference. That's going to be in degrees Celsius. So I'll just draw it as I'll just say C. Okay. There's a degree sign there. So we're going to find that generally the specific heat capacity of anything is going to be most commonly expressed in joules per gram per degree C. Now let's prove that here, okay? If I go and I write in here that this has units of joules, and you know what? I'm going to do it in Alex speak, all right? Joules per degree C. Now, what they'll do is, because it's in the denominator, they'll say it's times degrees C to the -1 times grams to the -1. You don't have to write it that way, but you'll probably see it that way. So I'm just kind of giving you a heads up. All right. Now, if we cancel the units here, there'll be joules, doesn't have, it's just joules on the left. But if we go ahead and say, okay, what's going on with grams? On the right side of the equal sign, mass is in grams, but specific heat capacity is in inverse grams, so they cancel out. Delta T is in Celsius. Specific heat capacity is in inverse degrees Celsius. So this is the most common expressed units, joules per gram per degree C. So keep that in mind when we get our result today. We've got to have it be in those units. Now, you might see calories instead of joules, but they said joules. Now, here's how we're going to solve this, okay? These two things are going to trade heat. The warm piece of aluminum is going to give the water heat. So if I could draw a little arrow out there, you know, a little tiny arrow, what you got? You got your sample. It's losing heat to the water. Now, why is it losing heat to the water? Because warmer object is always going to give the cooler object the heat. All right. And you can look at it the other way, is that the cooler object is going to accept the heat. So the way you set these up, we'll call it Q, the heat, Q aluminum. All right, I'll put it in subscript. Q aluminum is going to be equal to minus Q. Okay, let's talk about what the heck that means. Minus Q water. And that's because the delta T is going to have opposite signs. The water is going to gain heat, and the delta T is going to be positive. The aluminum is going to lose heat. The delta T is going to be negative, final minus initial. Now, to be honest with you, you can get away with forgetting about the equal sign or the negative sign here. That's not going to burn us like it would in other topics. We'll just remember that there's no such thing as a negative specific heat capacity. But if we set this up now, we could say Q, not Q, but Q aluminum is equal to M aluminum. All right, now lowercase m aluminum times C aluminum times delta T aluminum. All right, and that's equal to, and by the way, you could put the negative sign on either side. It doesn't really matter. It's got to be there. And like I said, you can kind of get away with it not being there. But okay, so that's equal to M water, C water times the delta T of the water. Now, one thing I noticed is I don't think they really said in the problem, of course, I didn't really read the problem yet completely thoroughly, is they didn't really give us the heat capacity of water. I assume that they want us to look it up. All right, so that's pretty standard here. We can't proceed without this. There is some unnecessary information, and nothing here is a gas and compressible. So let's just go ahead with the assumption that they said, okay, guys, go look up the heat capacity of water, because otherwise we can't do this. And you can go look in a table. It is 4.184 everywhere in the world. It is 4.184 joules per gram per degree C. All right. So now let's keep track of what we have in our inventory. Okay. What did they give us? They told us how much the mass of aluminum was, 50.9 grams sample. We don't know what the heat capacity of aluminum is. That's the whole punchline of the whole thing. They did give us enough information to find out what the delta T of aluminum is. So we can say that we have the ability to do that. Okay, we can get delta T of aluminum. They told us that the mass of the water was 150 grams. They didn't tell us, but they should have. Thanks a lot, Alex, for the confusion. That heat capacity of water is, it's because it's calorimetry is usually done with water. Not always. Sometimes they use other liquids, but okay, I guess they assume that we know that it's going to be water. And the delta T of the water we can find because it went from 22 degrees 26.5. Cool. What did I forget? I forgot to put a negative in there. Did I want to put it on the left or right? It don't matter. Let's put it on the left this time. Okay. I'll change what I put up there. No, I'm not going to just, it has to be somewhere depending on what you're calling the system. You calling the aluminum the system? You calling the water the system? It don't matter. It's going to have the delta T of one is going to be positive and the delta T of the other is going to be negative. Cool beans. So let's do this. If you're a rearranger, what we can do is we can solve for C aluminum, just throw all these things together. But while we're at it, why don't we just go ahead and get a value for delta T of aluminum and delta T of water, okay? Okay, watch out now. This is final, T final minus T initial. So what was the initial temperature? And we got to pay attention. You got to be very closely paying attention to these things because you got to say, okay, what am I talking about? I'm talking about the aluminum. You got to read this carefully. Read it slowly. So the aluminum was initially at 95.7 degrees. And then finally, both of these objects ended up at 26.5. So this particular thing, the aluminum, is going to be final 26.5 degrees C minus 95.7 degrees C. All right. What does that equal to? That's going to be 26.5 minus 95.7 is negative 69.2 degrees C. Okay. Let's do the delta T of the water. T final minus T initial. See, the final is the same for both of these because that's what happens is they both end up at the same temperature, 25 degrees C, 26.5 degrees C minus 22.0 was what the water was according to the problem. And so that would be 4.5 degrees C. Now, you'd look at it and you say, hey, that water changed by a lot less than the aluminum did. And that would be very much expected. Let me explain why. Not only does the water weigh 3 times as much, so there's 3 times as much matter there, but I am telling you guys, water is like the top notch, the upper echelon of heat capacity. It is royalty of heat capacity. If you've ever been in cold or hot water for a long period of time, you know what it can do to your body temperature. All right. Don't get me started on the ending of Titanic when Leonardo DiCaprio somehow belted out a huge monologue while in freezing water, proclaiming his love for his lady friend, when really in real life, in that cold of water, his monologue would have been like, you know what I'm saying? So water is always the highest in any common substance in heat capacity. So that's why it absorbs a lot of heat per degree Celsius change. That's what specific heat capacity means. All right. So now let's take these newly calculated delta T's and let's do some rearrangement here. Okay. You know, if you're a number cruncher and you like to just put it all in at once, we can say the heat capacity of aluminum, and we are going to keep track of the units to make sure we don't, we check ourselves before we wreck ourselves. So what we're going to do is we're going to say that would be if I divided both sides by mass of aluminum and the delta T of aluminum. So let me just put in symbolically what it means, and then we could feed it numbers, okay? So that would be, the mass of the water times the heat capacity of the water. None of that has changed. I used capital letter C for specific heat capacity. It's usually a lower case, but whatever. I was feeling it there. So we're going to go and say that that's what that is. All right. Then divided by both sides to cancel out, we're going to have the mass of aluminum, all right, divided by the delta T of aluminum. All right. Hopefully I'm not losing anybody here. We're just doing some basically just isolating C aluminum by dividing both sides by the mass of aluminum and delta T of aluminum. I just don't have much space on my screen here. And so there we go. Now, let's feed it numbers and see where we get. All right. I'm going to go ahead and just get rid of my. No, let's go ahead and keep it the way it was. That was water. Okay. So that is down here now. Now, for the sake of this, I'm expecting the specific heat capacity of aluminum to be much lower than that of water because, like I said, water is the highest heat capacity of anything common, and metals are usually pretty low heat capacity. So I'm going to get a number much less than 4.184 when I get all done with this. Then we've got to round it to the correct number of significant figures. Let's talk about that in a little bit here. So this is going to be equal to, in the numerator, this is going to be 50. You got to be really careful. I almost goofed up there. 150.0 grams. All right, that's the mass of the water. Specific heat capacity of water, 4.184 joules per gram per degree C. I'm not going to do the negative one thing. I'll do it a little bit different just to give you a little flavor for that. What was the delta T of the water? Positive 4.5 degrees C. Okay. What's in the denominator? I'm going to have the mass of aluminum, 50.9 degrees C. Negative. No, sorry. Negative comes up next. I was thinking about something coming up. 50.9 grams. Okay. What is the delta T? That's where the negative was, right? And I didn't put it up above. That's a bummer on my part. Sorry about that. 26.5 minus 95.7. Last I checked, that's a negative number, right? So this is going to be negative 69.2 degrees C. And then remember, we had a negative in the equation. And so when I went over here, I should have put the negative there. And you see the negatives cancel out, double negative. And like we said, all specific heat capacities are positive. Ain't nothing that you put heat into and its temperature goes down. All right. So if you'd have forgotten the negative sign here, you'd have been cool on this one. Not the next one we're going to do. You'd have gotten burned. All right. Let's keep track of our units here just to make sure that we did the right thing. So let's go through and say, okay, grams, cancel grams. Degrees C, cancel degrees C. What do you know? We get joules per gram per degree C, just like we're supposed to get over here in our answer. Now let's get a number and correct number of significant figures. I've got 4 significant figures in the mass on the denominator, or in the numerator, excuse me. Specific heat capacity is a table value. You can think of that as being infinite significant figures. It's not a measured number, so we ignore it. There's 2 significant figures in 4.5 degrees C. There's 3 and 3. This should have 2 digits when we get done. You always round it. We're multiplying and dividing to the smallest number of significant figures. So I'm going to go ahead and take 150 times 4.184 times 4.5 divided by 50.9. I screwed up on my calculator. I hit the wrong button. Divided by 50.9 divided by 69.2. And I'm just going to give you, I'm going to barf out what my calculator said. My calculator said this was going to be 0.8018, and then a whole bunch of other crap that we don't need. 1810, 19, blah, blah, blah. I've got to make that 2 significant figures. And so when I put my answer in the magic box, I'm going to call it 0.80 in the box. They were nice enough to put the units in there for us, which is great because putting the units in something like this is kind of a pain when it's got compound units. Capiche? We good? let's do another, because that's what Alex is about. It's just repetition. So I'm going to go and say, let's take a peek at another one. Let's run it through. Maybe they'll have a different substance. If it isn't, I'm going to keep going until we do get a different substance, because that, if it's another aluminum, I don't really want to do that. Okay. So here we go. And scene is over with. Let's see. Let me go hit the show another button. I want to make sure it says a different substance. Okay. I don't want aluminum again. Sorry, I'm going to hit another one. I don't want it to be aluminum. If it's just a quartz, cool. Sounds expensive, frankly. So, yeah, quartz. Now, let's think about this. Where is quartz going to be? Certainly less than water. And so I would say quartz is going to have a higher specific heat capacity, because if you heat up glass, it don't look hot, but it's still hot. You know, you touch it, like if you do that, I'm going to guess that quartz is higher than the heat capacity of aluminum, but we're not going to leave anything to chance. So very similar. They even put the numbers in the same kind of places. There's 57.3 grams sample of quartz. And then now the cup has 100 grams of water. So the masses are a little closer together. The quartz is at 88.9 degrees. The water is at 20 degrees. And then they both end up at 26.2. Cool. Let's do this. Let's go ahead and say, okay, Q equals MC delta T. You know, and if this makes you feel good to get lubricated, write it down. It's easy to remember. MC delta T. Think of it. It's like what a hip hop star should be named if it was a chemist. You know, have a big thermometer hanging around a gold chain or something like that. Q equals MC delta T. We're going to go ahead and say Q quartz. Q quartz equals minus Q water, or the other way around. Let's go ahead and say that means M quartz times C quartz. And they didn't give it to us, but I'm going to assume that they're assuming that we're going to look up the delta T, or the specific heat capacity of water, 4.184, right? C water is 4.184 joules per gram per degree C. That's a given. Otherwise, this is going to be really impossible. So that's going to be equal to minus Q, or M water, excuse me, M water times C water times the delta T of the water. I put the negative on the right side of the equal sign. It don't matter, okay? And let's go ahead and do the delta T of quartz. Quartz was warm, and then it ended up cooler. So the delta T of this is going to be, both of them end up at 26.2 degrees C minus the initial. So this will be a negative number. This time the negative sign will be on opposite sides of the equal sign. So, you know, whatever. So it'll be negative something, 26.2 minus 88.9, negative 62.7. Okay. What's the delta T of the water? The water started out cool. That's how you do calorimetry experiments. You know, and this is a way you can identify something if you had to. The water ended up at 26.2, as they both did, minus 20. It was 22 last time, and that was bugging me. So the delta T of the water was a little bit bigger this time. But remember, there's less water in this particular problem, so I'm not bothered by any of this. Now, frankly, gang, if you wanted to, you get rid of the negative sign completely, because, you know, it's on both sides of the equal sign. Just slash it out. I'm going to ignore it for the rest of the time here. And so if we're going to go, we're going to, solve for CQ. That would be if we divided both sides by M and then delta T on both sides, right? I didn't do it last time, so I felt bad about it. M delta T. So let's solve for what symbolically C quartz is. C quartz is going to be, well, the numerator will be the same. It'll be MW times specific heat capacity of water times the delta T of water divided by the mass of the quartz and then divided by the delta T of the quartz. And then we just have to be careful about how we're going to put our values in there. We're not going to, don't mix them up. If you get something greater than 4.184, remember that water is the highest heat capacity of any common substance. And that means what we did is we jacked it up by, I've seen it so many times, gang, you get your delta T's wrong. So for example, if I put the 6.2, I have to say it first. I haven't really figured out where what goes. All right. If I put the 6.2 on the bottom instead of what's going to end up being on the top, then that's going to be bad, and that's what we call in science jacking it up because you got it backwards. So let's be careful here. The mass of the water was 100.0 grams. Okay. Specific heat capacity of water, which we're still assuming was given 4.184 joules divided by grams divided by degrees C. The delta T of the water was positive 6.2. We're not worrying about the negative sign anymore. And then divided by the mass of the quartz. There's less quartz in terms of mass there. The mass of the quartz was 57.3 grams. The delta T of the quartz was negative 62.7, but remember I said that they canceled. So 62.7 degrees C. And if we look at what units survive, it's the units of heat capacity because masses cancel, grams cancel, degrees C cancel. And I am going to, just eyeballing it, get a value that is less than 4.184. Let's see if my prediction about it being, greater than aluminum is true. I'm not so sure it is going to be. Oh, and then two significant figures because 6.2 is the lowest number of significant figures. You've got 100.0's got 4. The heat capacity of water's got infinite because it's a table value. It's not a measured number. 6.2 is 2. The other ones have 3. We got to trim this to 2 significant figures because it's nothing a bigger bummer than being wrong for the very last thing because you put too many units in. So 100.0 times 4.184 times 6.2 divided by 57.3 divided by 62.7. And I was wrong about being, I guess quartz is lower in heat capacity than aluminum. So that's me just trying to show off about how much I know. Quartz is a relatively obscure substance. And of course, it's joules per gram per degree C, unless you have a watch, a fancy watch. What am I going to do? Then it's not obscure. I'm going to trim this to 2 digits. So that's going to be 0. Remember, the 0 doesn't count. Okay. 0.72. So the answer to that one is 0.72. Well, and if you do the other ones, that's the thing about Alex. Let's say you do the other aluminums and you got 0.8 and it told you you're right. Cool. You should pump your fist at that because you just got really lucky because now the answer is 0.8 because you got it right when you said it was 0.80. Here, now you get quartz and you're like, eh. But remember, most substances have a lower specific heat capacity than water. And so just keep that in mind. If I jacked up those 2 temperatures, well, and I put 62.7 on top, and 6.2 on the bottom. That would have been a double whammy of like 10 times 10 times or something crazy. I would have got a big number. And let's see what that number would have been before I let you go. You're probably already gone. 100 times 4.184. This is the what would happen if I jacked up the temperatures. And then let's say wrongingly, I put times 62.7, and then I divided by 57.3 wrongingly, and then I divided by 6.2. I would have got 73.8. Ain't nothing got a heat capacity of 73.8. When water, the most highest heat capacity substance that's common in the universe is 4.184. And so the only thing I wish Alex would have done, I wish they would have told you that you can look this up somewhere, because they did give it to us. So I assume that they wanted you to look it up in their table or something like that. That's all I got for you today. I'm going to actually film another one where we do the what's the end result temperature thing. Ooh, that's a tough one. And so I will catch you next time. And don't fall in cold water like Leonardo DiCaprio, and that was sad because I don't know. Sorry. I should have just ended it there. See you later. Bye.